Yeah, so as Tanya mentioned, my name is Marissa. I do not have a PhD, so just a master, so just Miss is fine. I am a researcher at the Cold Regions Lab at Corel, but I do a lot of my work with the FUNWAVE team at CHL, including Gabby, Michael Lamb, Fabian, Abby, and I had 2 students this summer who I'll talk about as well. And then while Matt's on his detail, we're kind of it for the FUNWAVE team while Matt is doing his rotation in the Pentagon. So if you have any FUNWAVE related questions, you can come talk to us. So today, what we're going to be talking about is kind of a culmination of some of the work that the 2 students, Levi Cass and Amy Bredis, have done this summer with respect to looking at wave transmission, one of the wave responses of interest for this particular project within CIRP. So looking at wave transmission in FUNWAVE, and specifically there are 2 methods for which to incorporate structures or a reef-like structure in FUNWAVE, how they perform in terms of wave transmission. That's what we're going to be talking about today. So just, I guess, a general project overview. You can see our timeline in the upper right-hand corner. As Tanya said, we're kind of coming towards the end of our 2nd year in terms of funding cycles, in terms of funding years, with 1 more year to go, starting in January of FY24. So this overall, the goal or objective of this project is to provide practical guidance for implementing permeable and impermeable coastal structures in FUNWAVE, specifically for the use of the rapid environmental assessment of these designs and design alternatives for coastal engineering applications. So our primary, someone's got a hot mic out there. If you could just general reminder to mute, that'd be great. So the purpose of this presentation is to kind of like take that existing body of literature that exists around coastal engineering and what we know about wave responses over submerged and emergent coastal structures, and how do we bring that into FUNWAVE in some way, and how to make FUNWAVE more of a, or allow FUNWAVE to exist in this operational environment for these types of applications specifically. And it's not exactly one-to-one, so there is some finessing here, and that's what we're trying to kind of nail down. So in terms of technical goals, it's defining those numerical parameter equivalents that you would put into FUNWAVE in order to replicate a real breakwater, not only its design, but also its respective wave attenuation effects. So that way you can properly hindcast and then eventually forecast wave environmental conditions in your area of interest. Ultimately, providing practical guidance for all sorts of levels within the FUNWAVE model is to kind of enhance the accessibility and usability of the model for users of all levels and all sectors. And hopefully this will help us all stay resilient against coastal storms by adding this into the existing toolkit and suite of tools that everybody has available. Can this be another one to kind of help fill in the gaps where needed? And just a big shout out to our PDT members who have been with us since 2020. Really appreciate your time and attention and your feedback. Really, we're gearing this product towards our USAFE district partners and trying to make this more usable and accessible for them in particular. So having their participation has been amazing these past couple of years. So as Tanya was mentioning, this is one of 2 FUNWAVE work units in the CIRP portfolio. Mine is practical wave response guidance, and then there's another one that Matt Millay is leading and that Michael Lamb has been monitoring and managing while Matt's on his detail. in terms of extending FUNWAVE into more dispersive environments and adding a variable water level. So I can say that at this point, we're on similar timelines between the two projects. So at this point, the variable water level is available in the latest beta release of FUNWAVE if you'd like to play around with it. And documentation has been updated on the wiki for your guidance as to working with that. And in general, as well, there's a FUNWAVE component in a new Engineering with Nature project that was kind of kicked off in FY22, but didn't get really a start until FY23. And this is looking at how do we add and computationally model oyster reef breakwaters. So kind of similar to this regard, but oyster reef breakwaters are lesser well studied. We know less about their hydrodynamic and let's say velocity profile and turbulence properties. So we're slowly working through there to see how we would not only add our traditional coastal structures, but also potentially natural and nature-based features into FUNWAVE as well. So what is FUNWAVE? Just a general brief overview for folks who may not be familiar. So FUNWAVE stands for Fully Nonlinear Wave Model. It is a nearshore, so the shallow to intermediate water regime model. It's phase resolving, Boosanesque type numerical wave model. So it's really good in the nearshore coastal processes, especially around complex bathymetry or complex topography. Very good at run-up, overtopping, diffraction, refraction, full reflection, and the like. So very good in that space. And it is, in terms of like the levels or classes of models, you know, if class 1 is more towards the analytical or an empirical model versus class 3 is up with your full Navier-Stokes like computational fluid dynamics model. FUNWAVE is kind of towards that higher end in terms towards the CFD modeling, but it is still a bridge between your phase average models and your full CFD model. So you can kind of use that as an intermediary step if you need more fidelity, if you need more details about your specific environment. You can kind of step up from there. FUNWAVE is kind of sitting nicely in the middle there. FUNWAVE is fully parallelized on the high performance computing machine, so with our DoD HPC fully available, and we also have a web-based interface, web-based application through the DoD HPC portal where you can set up and run FUNWAVE simulations right from a web browser that we're continuously currently developing to make it more user-friendly. It is open source, and this was developed in collaboration with the University of Delaware, and we do have it is managed by the University of Delaware still, and we have a full comprehensive wiki page also managed by UDEL that we constantly update, as well as the University of Delaware constantly updates as well. So that's kind of a little bit of FUNWAVE in a nutshell. If you have more questions, feel free to check out that comprehensive wiki, or feel free to ask me about it later. So with respect to this project in particular, we are looking at providing some wave response guidance over submerged and emergent coastal structures. And by wave responses, we're looking at run-up and overtopping, wave transmission, and wave reflection. So for this particular talk, we're focusing on wave transmission. Mostly there are, in addition to wave response guidance, wave transmission, looking at how two different methods for implementing types of coastal structures into FUNWAVE that currently exist, that are native to the code already, and evaluating their performance in terms as using wave transmission as the metric to understand its limitations and applicability in the context of submerged breakwaters for right now. And hopefully this can inform some of that practical modeling guidance for the traditional structures, the impermeable submerged structures versus maybe a more nature-based solution or nature-based structure that might be more porous or more permeable than it is impermeable. So this will be the focus of the talk today, specifically for a 1D monochromatic wave simulation focusing on a submerged structure. So what do I mean in terms of wave transmission? There are a few, I guess not a few definitions, but a few like physics, a few things that contribute to wave transmission in the literature, right? So what I mean here is that wave transmission is relating that portion of wave energy that is transmitted past or through a submerged or emergent structure compared to the incident wave conditions. So in the upper right-hand corner, we can see a graphic from the ROC manual kind of explaining that, where you have your incident wave conditions. Maybe that structure is submerged or emergent, and it has a certain crest width B and a certain freeboard RC. And through the rest of this presentation, I will refer to freeboard as the letter F. So you'll see that RC and F will be the same throughout the rest of this presentation. But that freeboard is that gap or that distance between the structure height and the still water level. And that plays a significant role in wave transmission here. So I mentioned in the literature that there are different phenomena that contribute to the total wave transmission metric or response, and those three are usually overtopping transmission. And again, this is in reference to wave heights propagating over or through over a structure onto the lee side, and not necessarily that overtopping rate or volume. So there's overtopping transmission through the structure, and then we consider diffraction around the structure. In this particular study, for this particular project, we're looking at just overtopping transmission. FUNWAVE does not have a permeable or porous media per se, so transmission through the structure is not accounted for here in theory. We'll talk about that later. And that's actually one of the difficulties throughout the literature, is being able to separate that transmission contributions from overtopping versus transmission through the structure. In our physical modeling studies, it's kind of hard to distinguish. So for right now, we're focusing just on the overtopping transmission, and specifically kind of more or less recreating or testing, solving for that wave transmission coefficient, which you can see on the bottom left-hand side, which is just relating that ratio of total energy on the shoreward side of the structure compared to the total energy, incident energy on the seaward side of the structure. And I'll use the term KT through the rest of this presentation, and for our purposes, we use just the ratio of transmitted to incident energy as our metric here. Okay, a little slow on my end. So I mentioned that there is a comparison of two methods, and there are two ways to incorporate structures in FUNWAVE. One method is with direct modification of the bathymetry, and this is the impermeable method. And then there's a breakwater file, which is an internal dissipative sponge layer, which is our permeable method. So we're looking at testing these two methods to see how they perform with respect to wave transmission. So the bathymetry modification method is you have a base bathymetry, and you're taking it and putting in a structure and modifying the bathymetry to match a certain structure shape and size. Whether it is that slope, that crest width, and that freeboard is completely controlled here, so you can maintain that explicitly. And you can also incorporate a bottom friction over that layer and over sections of that layer, for example. There is a variable bottom friction that can be applied as well to help simulate or replicate the roughness of a certain structure type, for example. Now with the breakwater file, the permeable structure with the breakwater file, you define a location in the domain and a width of that internal dissipative sponge layer. And that sponge layer is through the water column. FUNWAVE is a depth average model, so it's just at a certain location, a certain size with respect to the wavelength direction, so as the waves pass through it. Now, because it's just a sponge layer through the water column, it's not a direct comparison to maintain the structure or a physical structure shape and size. It's more its effect, like what the wave transmission or wave attenuation effect that you're looking for, you can replicate with the sponge layer. So there are two parameters that go with that. I mentioned the width. So how wide is it with respect to the wavelength, and then the strength of that sponge layer. You can think of this sponge layer as like a mathematical mesh through the water column, and as you increase the strength, you're increasing the like the size of those holes that the wave has to go through, for example. I have a figure later in this presentation that kind of illustrates that as well. So these are two methods for incorporating structures in FUNWAVE. We know that we're looking at wave transmission. So let's set up our study and let's see what we did this summer here. So I mentioned two ways of incorporating structures, therefore two sets of simulations. One with modifying the bathymetry only. So that's that gray section of the bathymetry in this upper right-hand corner. And then one set of simulations with the dissipated sponge layer only. And that's that orange, those orange-red dots through the water column there. Again, we only did one or the other, not both, not yet. So when I show variables later on this slide, variables that are colored in gold or yellow will refer to variables associated with the bathymetry modification method, and then variables shown in green will be related to the sponge layer permeable method. So this is an example of one of our computational domains and how we set that up, just a regular idealized flat bathymetry with that reflex structure or submerged structure in the domain with plenty of room on the shoreward side of the structure to prevent reflections from the end of the domain where our waves are propagating from left to right here or west to east locally. So we wanted to set up some wave conditions that we would typically see or are common for a protected water body where these more submerged or nature-based solution, nature-based features might be, and compared as opposed to an open ocean environment. So in a protected water body, we decided on these typical windy and stormy conditions, and we are changing both the wave period, the wave height, and water depth here, kind of scaling them up. These were our input wave conditions that we tested in each simulation. In terms of constants, we kept the wave height relative to the water depth at a ratio of about 10%. So the wave height will not exceed 10% of the water depth. Our relative crest width with respect to the wavelengths, again, this is just for the bathymetry modification method. We kept that for right now at 0.03% of the wavelength. And the variables that we played around with and looked into during this study were the relative freeboard. Again, that's that gap between the height of the structure and the still water level. So we played with varying that height of the structure. We played with the coefficient of friction, so that bottom friction over the entire structure to simulate that roughness of a structure. And then in terms of the dissipated sponge layer, again, we only have two parameters to play with here. So it's that sponge width, testing different sponge widths, as well as the strength. That breakwater absorption coefficient is the strength of the sponge layer. So those are the variables that we played with. And to assess the performance, we looked at wave transmission, right? And we looked at these two gauges, one on the seaward side of the structure and one on the shoreward side of the structure, about 4 wavelengths separated from the structure. So we see that gauge 6 is going to be our incident wave conditions, and gauge 134 is our, will collect our transmitted wave conditions. Now, in FUNWAVE, you can input these virtual gauges, internal gauges inside the domain, and you will have, at a higher temporal resolution, you can have surface water elevation and UNV velocities at those locations. So this is what we pulled from. So we have this time series of the surface water elevation. We'll convert that into the frequency domain by taking the Fourier transform in order to create this power spectral density. From that spectra of wave energy, we'll sum it up to compute our total energy. And again, if we do follow this method for the transmitted gauge versus our incident gauge, we'll get our transmission coefficient. So this was our study design. And we had two hypotheses that we were looking to test. Again, one is that how do we relate the sponge layer variables to our physical variables or our physical structure properties. And we were thinking that maybe the breakwater absorption coefficient could be analogous to the relative freeboard and that gap between the structure height and the still water level. And maybe the sponge width is analogous to the crest width of that structure. And again, that breakwater absorption coefficient, as a graphic here, is controlling the strength of that sponge layer, where through the water column, that mathematical mesh gets finer and harder to go through, essentially. Our second hypothesis was focused more on just the bathymetry modification method, where maybe our bottom friction will have less of an effect on energy transmission when the structure is more submerged or at a higher water level, and then it will have more of an effect on energy transmission at shallower freeboards or when the structure is approaching that still water level, is closer to that still water level. So those are some of the things that we tested. Without further ado, let's jump into what we got. So I'll just show a few videos from the impermeable method and then the permeable method. So in this video, we can see in the upper right is the whole domain with a structure, an impermeable submerged structure with a freeboard about 0.2 meters. And as waves with those wave conditions listed on the bottom there pass, propagate to and over the structure, we have a zoomed in video on the bottom showing what those waves are doing on the lee side or the shoreward side of the structure and how we're seeing how those waves are changing. And if we were to take and break this down into the frequency spectra, what we're really seeing is the nonlinear effects of shoaling and breaking. And this is shown as dispersion in our power spectral density plot over on the bottom left. So in that image, the blue curve, again, is that gauge 6. That's that gauge on the seaward side of the structure. And the orange curve is that gauge on the shoreward side of the structure. So we see that the energy from the peak frequency, this is a regular wave case, a monochromatic wave, so we would expect to see all of that energy in that peak frequency. We see that after the structure, that energy is transferring to higher harmonics. And this is actually, it actually agrees with what we've seen in the literature between Ahrens and Vandermeer, saying that once, specifically for overtopping transmission, that as waves pass over a submerged structure or a low crested structure, that energy will likely transfer into higher harmonics versus energy or waves passing through the structure or transmission through the structure, you'll find that energy transfer to lower harmonics. Again, this is an impermeable feature, so waves are just passing over the structure, and we're seeing that transfer of energy into the higher harmonics of that frequency. And based off of examples or cases that we've seen in the field, this type of dispersion is actually more representative of field conditions of what you might expect to see in your real-world application. You'll expect to see, as the waves are feeling changes in bottom bathymetry, waves will be a little bit more dispersive over these features. And I guess I will point out, if you can see my cursor, that as the waves are passing over the structure, there is a certain section where these waves are maybe more dispersive, and then once allowed to propagate again in the idealized bathymetry, that energy starts to transfer back into that peak energy, into that peak frequency, just based off of just looking at the waveform. So it looks like, depending on where you put your gauges in the numerical simulation, but maybe also in a real-world application, you might see different wave transmission responses. So that's something to consider that we can look into in the future. So that's the impermeable, our bottom bathymetry method. Let's look at our permeable layer. So again, we don't have a physical structure here. We have similar wave conditions, except this time we're using a thin or a narrow sponge with a breakwater absorption coefficient or strength of 10 here, where that yellow bar is. And immediately you can just see there is just really a dissipation of that of the amplitude of the wave as it passes through this feature. And that's what we might expect. So through this dissipated sponge layer, it is dissipation only. And we can see that in our spectral density plot, where there is a significant reduction of energy in that peak frequency, and there is no transfer into the higher harmonics there. So in theory, this could be representative of porous structures. Maybe if we use them in use the sponge layer in combination with an impermeable feature, maybe of a different shape or size, to incorporate some of the dispersive effects, while adding more dissipation effects as you need for your particular application or your particular field condition. So looking at our wave transmission coefficient, this is some of our hypotheses. So looking at the second hypothesis first, bottom friction having more of an effect on the energy transmission at shallow freeboards. So on this image, we have a relative freeboard on the x-axis and our transmission coefficient on the y-axis. And so on that x-axis, we have from more negative to less negative. That structure is becoming less shallow, so that freeboard is becoming smaller, meaning that it's getting closer to that still water level. And as we see that structure become closer to still water level, the colored dots on this plot represent the different bottom friction values that we looked at. So as bottom friction goes from the cooler colors, which is low friction, to the warmer colors, are a little bit higher friction, we are seeing that the bottom friction has more of an effect in controlling the wave transmission, kind of controlling some of that dissipation on the structure when the structure is less submerged. And we see that as the structure becomes more submerged, the bottom friction has less of an effect or contributes less to the overall wave transmission response on the structure. Now, I will say, so this is just for that, the typical wave conditions that we selected, so a period of 3 and a water depth, or 3 seconds and a water depth of 2 meters. Now, if we were to compare that to the other two conditions that we looked at, the windy and stormy conditions, so we still have this blue envelope here, where again, the top of that envelope is with the no friction case, and the bottom of that envelope is our high friction case or our added friction case. I'll compare this blue envelope to the other two conditions, and that's what we see here, where the windy condition is shown in the red envelope and the stormy condition is shown in the green envelope. And I'll just point out two things with this comparison is, one, towards the less submerged part, so towards the right of that image, we do see some convergence where no matter of these conditions, we are getting a similar transmission coefficient as that structure is approaching the still water level for all three of those conditions. Again, with the bottom friction being the control, like how wide that envelope is under each condition. And then I will say, is similar to, not exactly matching, but is similar to what we would see in that rock manual, that image that I showed at the very beginning of the presentation, where we have this curve. We're just looking at the submerged portion of that curve. Now, the second thing I'll point out is the red envelope and how for when the structure is more submerged, so we have a higher relative freeboard or a more negative relative freeboard, we actually seeing that red curve go above 1, which suggests wave amplification. So we have the wave energy or wave amplitude is actually larger on the transmitted side of the, or on the shoreward side of the structure versus the incident wave side. And so this is an interesting result, one, that wave amplification is happening, and FUNWAVE can model it. So, and capture that as well. So we are capturing that kind of wave amplification effect, and this could be especially important if your area of interest has wave amplification that you've observed in the field. It is possible to simulate that in FUNWAVE, and you can always look into that more. Those are two fun things. So we move on to our second hypothesis, or our first one, that trying to relate the sponge layer parameters to our physical parameters and what effect they would have on the wave transmission. Maybe the breakwater absorption coefficient is analogous to the relative freeboard and sponge width analogous with crest width. We didn't get to the crest width, so we're just going to focus on the first part of that hypothesis, looking at breakwater absorption relative freeboard. Again, on the left-hand side, you have that same figure of the typical storm case with a period of 3 seconds and a water depth of 2 meters, that blue envelope. And now we're going to compare it to the envelope on the right-hand side, which is for our permeable case, where now we have sponge width on the x-axis increasing in width and size relative to the wavelength. So this is a proportion or portion of a wavelength is the width. And this time on the right-hand side, our colored dots refer to the strength of the sponge layer. Again, cooler colors refer to a lower strength and warmer colors refer to a high strength. And our high strength here was a strength of 10. So again, a few things that we can point out here. One, it really seems that the breakwater absorption coefficient or the strength of the sponge has more significant contributions to that wave transmission response for narrower sponge widths. And if we keep that sponge width at the sponge strength, that breakwater absorption coefficient at a high value, say 10, the bottom of that envelope, there really is not much change, not much different in the wave transmission response that you would get from a narrow sponge versus a wide sponge. So I guess our recommendations moving forward is there's a lot of variability there. And in terms of using the breakwater absorption coefficient to fine-tune the strength and transmission properties of the sponge versus the width, we're seeing that that's more important. So our primary conclusions, no surprise, is that the internal sponge layer is in fact dissipative, and it's dissipative only. So we can use that to our advantage when we can. So sponge layers, we're not representing a physical structure shape explicitly, but we can mimic or replicate a certain response. If you're looking for a certain response, the sponge layer may be applicable here, and we would like, as a team, to have more data to compare to with actual porous structures to kind of verify the amount of how to relate actual porosity of a structure with, say, the dissipative properties of a sponge layer, for example. And the second primary conclusion is that our bathymetric methods are producing more of a dispersive effect with using bottom friction as an added dissipative effect. We are able to mimic the shape of a structure explicitly, and the bottom friction is in fact contributes more to the wave transmission response when that structure is less submerged versus when it is more submerged, or at a lower water level versus a higher water level. That is important for anybody in a particular area that has a tide cycle, which is most people, most areas. And then lastly, we're seeing an amplification of wave energy. We're seeing that that's possible for certain freeboards under certain wave conditions. So we're interested in reviewing that more and looking into it more. And ultimately, what we're trying to do is trying to mimic the images on the left-hand side or right-hand side, for example, right? How do we produce or replicate the responses of different types of structures using these two methods? Is kind of that is our goal. So from this work that we did this summer, again with our two students, we can come up with some preliminary guidance. So I've talked a lot about sponge layers and how they can replicate a certain kind of response that you're seeing. So for example, in your particular application, if you're observing waves of a certain spectrum on outside your harbor versus inside your harbor, if that spectrum doesn't really change, or if you just want that, what if that incident wave spectrum doesn't change and you did a dissipation only kind of obstacle or feature, you can use the sponge layer for that kind of project. Whether you know your certain wave conditions and you want to hindcast those certain wave conditions in a model domain you create and to calibrate the model in a certain way, figuring that out, and then you can forecast from there once you've calibrated the model and calibrated how to incorporate those the best solution for the responses that you're seeing and the structure of interest. And then mentioning that you don't have to use a wide sponge layer, so you can keep these sponge layers narrow, and it's really focusing on that or fine-tuning that breakwater absorption coefficient or the strength to have a more precise wave transmission properties. And then at this time, I guess we do recommend bathymetric methods to best have a one-to-one comparison or implementation of a physical structure to that will impact the transmitted waves if you're expecting wave dispersion in a real-world application. So if you care about what's going on, other wave responses at and around the structure, definitely use the bathymetric method. If you care less about what's happening at the structure and more maybe further away from the structure or feature of interest, you may be able to use the sponge layer kind of out the get-go. That's kind of what we come up with here. And I guess just to mention a few things looking ahead, we definitely want to look into a test suite that combines bathymetry with the sponge layer to see this porosity effect and kind of get a sense of what values corresponds to which wave transmission properties. So this was just a few tests of the monochromatic test suite of a few wave conditions and a few structure scenarios. We want to complete we will complete a full test suite of the all monochromatic wave conditions that we have in our test suite, and as well as irregular waves under different conditions, including different structure types and setups. And already I just scoped out the test suite just to complete the monochromatic test, and we're up to 400,000 simulations, combining all the different variables that we'd like to look at. So we will work our way through those and then move on, go through the irregular waves as well. And again, that is just for 1B. So this is just an example of the amount of work that goes into kind of developing this guidance and creating these figures. It does take dozens to hundreds to thousands of iterations of simulations to kind of get that response. Ultimately, we'll package all of this together to provide guidance on the sponge layer values, as well as our impermeable structure values in terms of wave transmission, and in general for this entire project, the other wave responses that we're looking at as well. It's kind of a full set. In terms of future work, we definitely need to look more towards verification and validation explicitly. So this work is more kind of numerical. It's looking at what FUNWAVE can do and what it's spitting out, or not spitting out, but how it's resolving everything and the wave responses that we can get out of FUNWAVE currently without any code modifications directly, for example. So reviewing the existing literature to see what laboratory data is available for us to verify against our bottom friction, so our roughness, porosity of structures especially, and if that proves, excuse me, if those data sets prove a little insufficient, we may or may not consider completing a physical modeling study in-house as needed to get the answers that we're looking for and to fill those gaps. And then ultimately, we may determine that we do need to incorporate a porous media into the FUNWAVE code directly, and that might provide a better wave solution, a better solution. Excuse me. Similar to what CMS Wave has. And that could be a potential statement of need in the future. Looking at you, PDT. Lastly, I'll just say thank you for your time and attention. We do have some tech transfer activities ongoing, and just a big thank you and huge shout out to my two students that were with me this summer, Levi Cass and Amy Bredis. They were the ones doing most of this work. Levi was funded with under CIRP to do all of the impermeable method, that bathymetric modification method work, and then Amy is our SSCP student who's sticking with us as well, who did all of the funded under engineering with nature to look at the sponge layer results, and this work wouldn't have been done without them. So really appreciate it and all the work that they've done. So thanks for your time. I'm gonna clear my throat now.